Ted Blanks, he is a guy who has been a member of this club for a long time. And you will understand this about him, like some of our other members, Ted does not restrict himself to just one membership of one club. You know what I'm saying? I mean, there are guys who have a reason to belong to another club, this is in their backyard, but they still like this club. There are people who go to the Tucson Club because they have an awesome site for viewing and whatnot. Ted Blank, you have the floor, my friend.
Thank you. Thanks, everybody. Nice to see you all. I'm Ted. This is my wife, Peggy. We're both members. And I have two presentations for you tonight. The first one is a short one to give you a quick update on the construction and design of our International Dark Sky Discovery Center that's being built in Fountain Hills. Some of you who brought telescopes to our Dark Sky Festival last Saturday night were able to see the building under construction next door. It's a lot bigger than I thought it was going to be. And it jumped up out of the ground pretty quickly. So I have a flyover video showing the construction over the last few months. A couple slides of pictures I took last night inside during construction. And then I'll switch over to the topic for tonight, which is going to be exoplanets. How you find them, what an exoplanet is, how we discover them, what they mean, and what they might mean for the discovery of life elsewhere in the universe. So I'll start with, there we are, the Dark Sky Discovery Center. This is a rendering of it. And I'm going to start with a little flyover video that I made over the last several months. Let's see here, I guess we click on it, maybe, there we go. This flyover video is taken from a drone that I fly about every 2 or 3 weeks over the site. And you'll see, and you can turn up the volume now, so we'll have some music. You'll actually see in about a minute and a half, about 7 months worth of activity on the site. Yes, if you want. That's August. September, November. That's what we call it, the darkskycenter.org. The reason that we mentioned this is there's really going to be nothing like this on the planet. This facility, I'm most proud of that thing called the Night Sky Exhibit Hall. In there, we're going to have about 20 exhibits showing people how the development of artificial light over the last 200 years has developed from campfires to using light to illuminate the night to what we have today, which is uncontrolled light at night, and some of the impacts that it has on humans, on animals, bird migration, turtles, lots and lots of things. And so we're going to be educating the people who come through our little exhibit hall there. And by the time they come out, they should be as passionate defenders of the night sky as everybody in this room is. We'll also have a planetarium. The observatory has a 20-foot ash dome. It'll have a 700 millimeter plane wave CDK 700 telescope for public viewing and research. And there will be a 140-seat auditorium as well, along with a classroom, 2 classrooms actually, a snack station and an outdoor viewing area where we're going to have 4, we've actually been donated 4 Celestron CPC-11 telescopes that will be able to be rolled out of our little storage room right into the private viewing area for folks to look through while they kind of wait in line to look through the big building. So lots of activity going on there. Here's a view inside the observatory. I was there when the dome went up. it was pretty exciting. They lifted it up with a crane and set it on top of the dome ring. The electronics are being developed right now, and the telescope's on order should be end of July. The telescope itself should be here. It'll be lowered in through that oversized shutter in the front. Planetarium dome there is gonna have a projection system, so you won't have to look quite so far up when you look at a planetarium show. The theater has tiered seating and projection and, 8K, all that good stuff in it as well. And the guys are busy working up there constantly. These are the components I mentioned: planetarium, the observatory, the stargazing terrace, the lobby, the inspiration theater, and something we call the Einstein Exploration Station. It's going to be like a light laboratory, high school physics lab, or an elementary school physics lab, where you can go and play with different exhibits that show you how light refracts, how the spectrum of light is spread out by a prism, so you can study the spectroscopy of distant stars and the elements that make them up. How much blue light appears as the color temperature of lights go up. So it's all going to be a hands-on place for kids to come in and just play with all these light exhibits to learn a little bit about it. Because what's the rule? What's the rule in the Army, Stu? No battle plan survives first contact with the enemy, right?
That's right.
You got to understand the enemy before you can win the battle. And so educating people about the components of light and how to control it will be crucial to getting people to understand how to protect the night sky and going forward. And we want that knowledge to spread and get excited so that folks can go home and update their outdoor fixtures, talk to their neighbors, and become passionate defenders of the night sky, just like we all are. We've raised $21 million so far, and we need about 7 million more. So anybody here has their checkbook? We are happy to take donations. So thank you. That is it for that presentation. Any questions? Yes.
Will the theater have 3D capability like ASU?
Good question. I don't know for sure if the theater is going to have 3D capability or not. I'll ask that question, and then maybe Stu can answer that online. Let's see. Yes, you're.
Actually, I had a related question. Is the theatre a projection system or is it an LED?
It's going to be a projection system.
Is it from Skyscan or?
That I don't know. I know they're working with a vendor who has developed, there's going to be 6 projectors, 6 8K projectors around the perimeter of the dome, and they'll seamlessly blend with each other.
Yeah, the stage is part of Skyscan.
That's pretty much all I know about it. If you
Is
have,
it overhead, does the seat pitch look like it was 45 degrees or 40 degrees? Is it
Yeah.
like a front projection or lying back?
it'll be lying back projection, but because the dome is going to be tilted 20 degrees forward, you won't have to lie back quite as far as you do in a dome that's strictly straight overhead. That's the plan, just for comfort. Yeah, Paul.
Is any of this going to be available for amateur astronomy organizations like PAS to have events there, like star party or presentation?
That will absolutely be my goal. Yes, absolutely. It's quite a ways to travel for folks who are centered around this spot. But the classroom, I'll work hard to make sure the classroom would be available for free to any astronomy club that wanted to meet there. So, yes.
Can I get time on the plane wave?
Get in line. The queue is already pretty long. People asking for that. Yeah, we're not sure how that's going to work, but we definitely will have it open at least a couple nights a week to the public.
Okay.
The plane wave is going to have, I don't have a picture of it in here. It's mounted up high, so we can get down low in the sky, but of course, then you'd have to climb a big ladder. The corrected Dahl Kirkham design has the actual image coming out, the pivot that so it's a triple mirror system, not 2 mirrors like a Schmidt-Cassegrain. And the third mirror can rotate around. So there's 2 pivots on either side. It's an Altaz scope. And on one side, there's going to be a camera selector with a rotator and 4 cameras. So you
What kind of azimuth?
yeah, we can have multiple cameras attached
On an azimuth out the side?
out the side.
Yeah, okay.
And then on the other side, there's a periscope made up of 2 telescopes that I would love to just take home myself. NP, Teleview NP 101s, I think, nose to nose to bring the image down. And so you'll be able to sit on a chair like this and look through the eyepiece at this height, even though the telescope's way up there. If you've ever been to Brancho Mirage Observatory, it's gonna be an almost clone of their setup. Went there and I fell in love with it, said this is perfect for
Seen that,
outreach
Yeah,
and for research, so,
that's
yeah,
cool.
okay. Oh, yes,
I hope that the pier, by the way, magnificent job, amazing that you built that while I was gone. I hope that that pier is separate from the floor and dug very deeply because you have traffic nearby and people walking on that floor.
you are so right. And of course, the design had exactly that. There's a 6 foot by 6 foot by 4 foot base to the pier that's about 6 feet underground.
Yes.
And then there's a 36-inch diameter column coming up, which the design made very clear was to touch the floor nowhere.
Very good.
Fortunately, when they poured the floor, they poured it right up against the pier. I know,
That's what it looked like.
right, but we fixed that. They came in, we explained that very carefully, and they came in with high pressure water jets, and they cut away a foot of the floor. And put in 2 layers of 1-inch foam as the design was suspected, and then
Yes.
we've got dirt and the concrete that nothing touches. So we should be perfectly isolated. Yeah, it would be crazy to build an observatory and not isolate the pier.
Oh, universities do that across the world.
So we know that, yeah. So no, we should be fine. Fingers crossed. I was there. I watched them wrap the foam around it, and I could see the foam when I look at the gap. So it's there, and it
Yeah.
should work out fine. But we had a bit of a heart attack and knocking it. Yeah.
You mentioned something about this telescope being available for research. Have any groups applied for time to use the scope for research?
The only one we've talked to so far is ASU. They're very interested in using this, and we understand that after 9 or 10 o'clock, when we all go home after a public event, we can push a button, click a button on our website, and ASU will be able to control the telescope completely remotely, operate it, take pictures, open and close the dome. It'll have weather sensors on it, so if clouds come or it rains, the dome will close automatically, the telescope will shut down. So yeah, that's in the plan, and I hope we'll have lots of people and facilities who want to use it like that, because we do need money to operate the facility. The town donated the land to build this building, and we raised all the money privately and through state grants. So we don't have a mortgage, but we are going to have expenses to operate, salaries, things like that, power, electricity. You have to actually pay for your water sprinkler connection, even if you don't have a fire. You have to pay for that every month to have that water available. So there are expenses to run the building, more than I ever dreamed. I have no idea what it took to do this. Okay, I'll close out of that and open up the other presentation.
If you want to unmute your speaker.
Okay. There we go. I guess what you have to do is turn the speaker on the Epson projector off, or maybe on your laptop. Okay. All righty. Well, so this talk is about what we call exoplanets. Exoplanets are simply planets around stars other than the sun. And yeah, that's fine. This is, well, of course, these things never work when you want them to. It's just a convenience. Yeah, I'll just go this way. There we go. So this is a big question, right? Are we alone in the universe? One of the people who thought about this question was Frank Drake. And Frank Drake came up with this thing that's called the Drake equation. How many people have heard of that, the Drake equation? Everybody. That's fantastic. So the Drake equation, Frank said, okay, if we want to figure out if we're alone, we can make some educated guesses, like Enrico Fermi used to do with his, you know, like if you could, one of the questions you might get at a job interview is, how many piano tuners are there in New York City? Well, how would you possibly answer a question like that? So you make educated guesses, right? Well, there's 8 million people, so that means about 1 million families, and maybe 10% of them have pianos, and you have to tune your piano once a year, and you come up with a number, and then you look in the yellow pages, and surprisingly, it turns out that the errors you make in one number that are too big are probably canceled by the errors you make in another number that's too small, and you end up with a number that's pretty close to the actual number of piano tuners in New York City. So Drake came up with all this, you know, and all of these would multiply together to tell you whether there were any number of civilizations greater than 0 in the universe that might have intelligent life. So the two we're going to talk about today are the two in red: the fraction of those stars that have planetary systems and the number of planets per system. So when you multiply those two together, you know how many planets there are in the universe. This is a protoplanetary disk, or an actual picture of them, and this is the evolution of a planetary system like ours. Here we are. There's Saturn and the 4 inner planets and so on. It starts with a cloud like this. This cloud of dust and gas has some rotational component to it. They typically do. It's perturbed by some kind of impact, maybe, or a supernova exploding nearby that causes it to begin to coalesce, and it eventually flattens into a disk. The physics of a rotating ball of gas always brings everything down into the middle, into a plane, and eventually most of the material ends up in the middle in the star, and the stuff that's left over, the last 1% or so, ends up in the planets. And the last 1,000th of 1% ends up in a planet like Earth. So here we are. If you've ever shown anybody around the Orion Nebula in your telescope, what I always tell people is that even though there are 4 stars in the trapezium, well, 6, but 4 that you can see easily, that are shining and illuminating that cloud, the Hubble telescope has peered into the Orion Nebula deeply and seen lots of protoplanetary disks forming in different places. All of these are scattered throughout the Orion Nebula, and not here where the trapezium is, but on all of the other areas. They just, their central star hasn't gotten hot enough to begin to emit light yet, or if it has, the news hasn't gotten here yet. It's only 1,500 light years away, so it's a close neighbor, but it's possible that 1,000 years ago, one of those stars lit up, and in only 500 years, we'll hear the news. These, and in images that we've been able to take of distant stars, we can see some pretty complex protoplanetary disk structures that give the hint that there are actually planetary disks forming around those stars. So the physics appears to be supported by images that we can actually take of distant star systems. So these are the 4 methods that I'm going to talk about today. Radial velocity, transits, direct imaging, and something called micro-lensing, which is really totally amazing. How many of you have heard of any of those methods? Yeah, I mean, a lot of us have read this in Sky and Telescope and in Astronomy Magazine. It's part of the popular pantheon of knowledge that gets written about a lot, but I have a friend in New Hampshire that I'll show you some of his images. He's doing this from his backyard in New Hampshire with an 11-inch Schmidt-Cassegrain, and he's able to actually detect exoplanet occultations by just staring at that star and making recordings. I'll show some of those later on. So the radial velocity method depends on the Doppler shift. It turns out that as a star and its planet orbit each other around a common center of gravity, the planet makes a big circle, but the star makes a small circle around that barycenter, that center of gravity out in space between the two of them. So when the star is moving towards you, its light gets blue shifted, and when the star is moving away from you, its light gets red shifted. What I mean is, you've probably seen images like this, where light from a star passes through the outer layers of the star's atmosphere, which are cool, and in cool gases, these various light wavelengths are absorbed, and so you'll see black lines where the last thing that this white light passed through was a gaseous cloud that absorbed only certain wavelengths of light, and these black lines will turn up in the spectrum. If you send that white light through a prism, you see the spectrum, but you don't see any light on those particular colors. And that can tell you what elements are actually present in the cloud of gas that was at that light passed through at the very last moment before it entered empty space and headed off for Earth. But on Earth, if you take the same glowing gas and you heat it up and send it through a prism, what do you see? You see the emission of the same colors that were missing in the star's spectrum from white light coming from the star. So these line up perfectly with each other for the same gas, and this is how you can make a catalog of spectra of every element on Earth that we can find, and then you can go search for those in the spectra of stars. And it wasn't that long ago that an English scientist made the quote that while we know lots about what happens on Earth, we will never know what makes up the stars because we can't possibly go there. And it was only 10 years later that spectral analysis was determined that we could actually tell the elements in the atmosphere of stars by analyzing the light that's reading us. Light brings us news of the universe. It's the only thing that does. And of course, it only travels at the speed of light, but that's fast enough. And here's an example of a spectrum with lots of different gases in it. So it's the job of a trained spectroscopist to figure out what combination of gases in the star's atmosphere gave you this combination of lines. It's not an easy job. But here's a little animation of what we're talking about. So here's our star and our planet orbiting this common center of gravity in space. So the star itself is making this small circle because it's much more massive. And see what happens. As the star is coming towards us, these lines get shifted slightly to the blue end. And when the star is moving away from us, they get shifted slightly to the red. And so by monitoring the spectrum of the star over time and comparing it constantly to the spectrum of gas here on Earth that isn't moving, you can actually see these lines go back and forth. And if the lines are going back and forth, that means that the star must be orbiting a spot in space. The only thing that can make it orbit a spot in space is if there's a planet somewhere out there that's doing the tugging and moving the star off of its own center of gravity into this space-borne barycenter. So that's the radial velocity method, and oh, it's working. And here's the radial velocity graph of 51 Pegasi over time. Let's see, I'm not sure what the phase. It's just phase. Okay, so this is a full cycle, and you can see that it's we've got red shift or blue shift, and the other one this one. And if sorry.
Graph, you could go back.
To
make that graph, how many in calendar days?
Yeah, that's
Is that a year's worth of data? Is that 5 years of
okay.
data?
Actually, so the period is 4.2 days.
They got that much data in just 4 days?
Yeah, so they took so from here to here is 4 days. So, we took about 100 measurements over 4 days.
Okay.
And probably over multiple days, because of course during the day you can't see the star. So you probably would do this over the course of a year and fill in some of these dots were probably taken at different months of the year, but eventually you could fill in the whole phase, the whole phase graph.
Got it. Okay.
Yeah. So 56 meters per second was the change in velocity towards us or away from us. And that was enough to cause those spectral lines to shift enough that equipment on Earth can actually detect its motion. Pretty amazing stuff.
There's not much uncertainty in that data, that's like.
Not very little, very little. Yeah, you can see the error bars are tiny compared to the phase. Right. And so if there was a civilization out in space looking at our sun with the planet Jupiter causing it to orbit a barycenter out in space, this is what the motion of our sun would look like to a distant observer in looking at our solar system. So there would be evidence that Jupiter existed based upon the motion of our star around that barycenter in space, so from year to year. So if you're a physics nerd, I don't have one of those, but I'm thinking I've got to put it up. Got to get one of those on my car. Okay, the transit method is probably the one you're most familiar with. That's where you stare at the star for long periods of time, and if a big fat planet happens to orbit in the plane of the light coming towards Earth, a tiny dip in the amount of light that you receive from that star can be seen while the planet's in front of it. And then when the planet goes off the edge of the star, the light goes back to its full intensity again. And here's a graph of what that might look like, sort of. Right, there's your light curve. So when the planet's here, you get the full light of the star. As it approaches, you get a drop in the light, and when it's in the middle, you get a big drop in the light, and then eventually light goes back to the full intensity. And if you see 3 of these at equal intervals, you know that you've got yourself a planetary detection. Now, of course, there are many planes of orbit around a star that don't include passing in front of the star. I think only 1% of planets at random angles would actually pass in front of their star to our perspective at any point during its orbit. So whatever numbers we get here, we can multiply by 99 to say there are that many other planets that we can't see because they just orbit this way, and we never see them pass in front of their star. But the few that do are the ones that we can detect through this transit method. Here's a Venus transit. I met this club in 2012 for the first time, talked to Terry. In New Hampshire, where I lived at the time, we had a big public event planned for the Venus transit in 2012, June, but it was cloudy. So the night before, I got on Southwest and said, "Where do you fly that it's clear?" And Southwest said, "Phoenix." I said, "Buy me a ticket." So at 6 the next morning, I was on the plane to Phoenix. I got here at 9 o'clock, came outside, blue sky, palm trees, 70 degrees. Actually, it was June, it was probably 100 degrees. But anyway, I came up here and you guys were out in the PVCC parking lot with solar scopes, and I brought my H-alpha scope, set it up, and was part of your outreach program. Next day, went home, and 2 years later, moved to Fountain Hills because I liked astronomy and I liked Arizona. And we have 29 cloudy days a month in New Hampshire. And here you have 29 clear days, so I'm in the right place. So here's the transit method. You see this. If you've gone to the Arizona Science Center, they have a cool display where they have a light detector and a light bulb and a little planet that you can turn a crank, and the planet will go around on a platform, and it'll actually pass in between the light bulb and the detector, and there's a graph of light intensity, and you can actually see it happen. Kids can turn the crank, make the planet occult the star, and do the transit and see the light curve on a TV screen. It's a big clunky display, and there aren't enough signs explaining what you should do. So when I was there, the kids were practicing who could make the planet go the fastest. That was all they were doing, and it had no scientific value at all. But if somebody was there explaining it, they could probably get something out of it. In 1999, this is the first detection. Nobody ever thought you could do this, but sure enough, there's planetary detection as well. Absolutely amazing. And my friend, John Gianforti, former president of the New Hampshire Astronomical Society, uses this C11 in his observatory to get data very similar to what we saw in 1999. You can do this from home, folks, with a big enough scope, dark enough skies, and pick the right star. And he loves doing this and publishes this data. Direct imaging, we can actually take pictures of stellar systems in distant galaxies and distant nebulas not too far away from us, and actually get images of the star, and then by blocking out the star with an instrument similar to a coronagraph, actually image the planets in the dust cloud around it. Sometimes we can actually watch them orbit. So here you can see some examples. There's a planet there, there's a planet there, planet there, planet there, planet there, planet there. So by blocking out the star itself and using speckle interferometry and lots of other stuff, this is only 120 light years away. So very close neighbor, right? That's what, 1/10 of 1% across the Milky Way. So this is a close neighbor star, and it gives us the ability to actually see the stars against the darkness of space by blocking out everything. Here we've got 3 stars visible here around around the star itself. Some pretty advanced imaging and analysis techniques obviously used for these kinds of things as well. 7 years of Keck observations here, you can actually see the planets orbiting their star. In 7 years of, so obviously these planets are quite far from their star. I mean, if this is only 7 years of motion, then we're talking Jupiter, Saturn distances as opposed to Earth or Mercury distances from their star.
Are they using just one of the kicks, or do they need both of them to get the resolution?
Oh, good question. I don't know.
Both, because it's speckle and geometry.
Right. Yeah, it could be both. Well, anyway, so 20, this bar, yeah, so 20 astronomical units is this distance. So this guy is about 30, this guy's about 20 astronomical units away. Jupiter's 5 and Saturn's 10, so we're talking Neptune, Uranus distances here. Pretty amazing. Beta Pictoris, here's another image of one of its planets. This is looks like it's about 2 years of data. Pretty amazing. Actually, you can see planets around other stars, so we're pretty sure. And so the bottom line here, just to give you the clue at the end, there are more planets in the universe than there are stars. That was the bottom line to me that made it so absolutely amazing. And Fomalhaut B, we can actually see in this dust ring here a tiny planet forming, and over the course of about 8 years, we can actually watch it move through the dust cloud, picking up more and more material as it goes, of course, getting slightly bigger and cleaning out, just like the moons of Saturn do for Saturn's rings, cleaning out this dust cloud eventually, right? Thousands of years later, all this dust will end up in planets, and we'll have ourselves a little solar system up there. And these debris disks are, other examples of stars that clearly have planets around them. The next slide is from Randall Munro, XKCD, right? How cool is that? This is his picture from 2012 of all 786 known exoplanets to scale. All right, so most of the planets that were discovered by 2012 were Jupiter-sized planets or larger because they block more light than a smaller planet. And during the early days when we had only certain sensitivity of instruments, you could only detect larger planets. So there are small planets that were detected, but the vast majority of these are Jupiter or larger sized planets as of 2012. This is our solar system right there. So that'll give you an idea. There's Jupiter right there. And a lot of these planets are way bigger than Jupiter. He is an amazing guy. So as of April of 2018, 3,758 confirmed planets around other star systems. Kepler mission was a mission that was launched into space to stare for many, many years at one small area of the sky and look for occultations, to look for stars passing in front of planets passing in front of some of those stars. So the same tiny area, there's I think it's in Cassiopeia, this tiny square of the sky where nobody actually could see any stars. They stared at that for years. That's in Cygnus. Yeah, thanks. And looking for transits of planets and found dozens, hundreds and hundreds. So monitoring the brightness of 150,000 stars every half hour, okay, for years and years and years. And eventually the gyroscopes in Keck failed, and the mission went into a backup plan mission, but it was very, very successful. Yeah, there it is in Cygnus. And these were these were the areas of the sky that it monitored every half hour. I'm not sure if it actually did them all at once or if it switched among them, but for about 4 years. So remember, go all the way back to Ptolemy. His understanding, what he taught, was that everything orbits the Earth, right, in spheres, in circles. We're at the center of all the orbits, and the speed of the planet is the same in every part of its orbit, because it looked like that to the naked eye. But when Copernicus came along, you know, he was the first one to suggest that it was not the Earth that was the center of all of these orbits, that it was the sun. We orbited the sun, even though people said, how can we be orbiting the sun? It doesn't feel like we're moving. We know different now. But he also believed that the speed of each planet was constant and that the planetary orbits were circles. Now, of course, you had to explain things like the retrograde motion of Mars. Well, periodically, as we pass Mars on the inside track, it appears to go backwards for a while against the background stars. Just like when you sit in the parking lot with your foot on the brake and the guy next to you decides to back out and you think your car is moving forward. It's the same thing. This planet appears, as it's going around the sun, suddenly it stops, goes backwards, and then it goes forward again. How do you explain that? Well, there were lots of complicated methods for trying to explain it away, but the easiest one is to suggest that Copernicus was right, that we're not in the center of the universe, that all the planets orbit the sun, and Mars is just farther away from us, and we pass it periodically, and it appears to go backwards for a while. Tycho Brahe in Denmark, he made the most accurate measurements of the positions of the planets in the sky against the background stars for decades. And when he was near the end of his life, Johannes Kepler went and worked with him for a while and had the idea that he wanted to get his hands on Tycho's data so that he could calculate what the orbits of the planets really were or should be or had to be based on the data. So good data allowed him to eliminate certain theories of like Copernicus theory or even Ptolemy's theory because the data, you have to match the appearances. That was Kepler's mantra. And the appearances, as you get more and more accurate measurements of the positions of the planets over time, certain theories predict something different. That theory has to go out the window. You got to come up with a new theory. Right? So Kepler he finally got his hands on Tycho's data, and sure enough, he was able to come up with his 3 laws of planetary motion. And planetary orbits are not circles, they are ellipses. The sun is not at the center, but it's at one focal point of an ellipse, and we go around the ellipse, and the speed of the planet is not constant. It varies as the planet goes around. It's faster when it's closer to its star and slower when it's farther away. So the 3 laws of planetary motion came out of the data that Tycho developed and carefully husbanded until he died. And finally, Kepler got his hands on the data and was able to make these incredible conclusions. We still use those today. So the Kepler mission, here's a drawing of it, and here's the actual spacecraft ready to be launched, being built at the JPL high bay. Here's the camera detectors, 95 million pixels. That's pretty good for the early 90s. Here again is the area of the sky that it was staring at. So its field of view was small, and it was a particular cone of space, and it only looked at that part of the sky. But there's another mission that I'll talk about later on. And so here are some of its results. See, here's a Kepler 4b, tiny planet, very small drop in light curve, bigger planet, bigger drop in the light curve, and then I'm not sure why this one's, I guess the star is a little dimmer, so you still get a bigger light curve because you had less light to start with. Lots and lots of positions. And you can see over the course of time between 89 and 97 when the first ones were discovered, most of them were actually discovered through the radial velocity method until Kepler came along. And now suddenly you're discovering them using the transit method. And it was very, very effective. And as I say, only about 1% of all orbits will actually pass in front of their star. So take these data and multiply them by 100 if you want to guesstimate how many other stars have planets that we can't actually see because they're not passing in front of their star. Yeah, all right, enough of that. The idea here is that we've got something we call the Goldilocks zone. If a planet is in a distance from its star and the star's intensity is such that liquid water can exist on the planet at some point, we have the possibility of life as we know it existing. If this planet is too close, like Mercury, there's no hope for liquid water to exist. If the planet's too far away, like the gas giants, there's no hope for liquid water. It's either going to be steam at one end or ice at the other end, but if you're in the Goldilocks zone, so for hot stars, that zone is farther away. For sun-like stars, it's at our distance, and for cooler stars, it's closer in around the Mercury distance. And it all depends on the size and intensity of the star. So we're always looking for stars that have planets in their Goldilocks zone, and it's a smaller percentage of all the planets that we've discovered around exoplanets. And these are the habitable zone, small habitable zone planets. So rocky planets in the Goldilocks zone discovered by Kepler. You can see there's about 20 of them in the early Kepler mission. This green band represents the Goldilocks zone of the star that this planet is associated with. They're not all associated with the same star. So lots and lots of candidates for life. All of these planets are opportunities for life because they're in a zone where liquid water could exist. We don't know if it does, but it's not too hot or too cold. That's the message here. All right, I also want to talk about a new mission called TESS, which was launched into space. So TESS had a different goal. Instead of staring at a single area of the sky, TESS looks at the entire celestial sphere. So it'll take pictures of a set of stars, and then it'll move and take pictures of another set of stars and do that, work its way around, do the southern hemisphere, and then come back and do the northern hemisphere again. So it's looking at the entire celestial sphere, but only stars that are close to us and bright, as opposed to looking at all the stars in that cone of space all the way out to the detection limit that Kepler did. So here's how TESS works. It's a little different than the Kepler mission. In this animation, you can see the camera here in the TESS spacecraft. Solar powered again, and it's got 4 cameras, and you can see how it is taking pictures of different areas of the sky, and then stepping to a new set area of the sky, taking more pictures, and eventually filling in the entire celestial sphere around Earth. And it did this for 2 years in its primary mission, which ended a couple years ago, and it's now in a follow-up mission doing the same thing. So TESS concentrates on brighter stars. You can see that there's magnitude 12. So Kepler looked at stars magnitude 12 and fainter, but TESS is looking at stars that are brighter than magnitude 12, all the way up to magnitude 4, just because they didn't look at the star for as long, so they had to use brighter stars to be able to see the star and the planets themselves. Since Kepler, 6,000 more confirmed exoplanets. Since TESS launch, 620 more confirmed exoplanets and 7,000 candidates that have to be reviewed. So very, very successful. There's TESS sitting on the pad. There's it is ready for launch. And here it is. And this is the follow-on to TESS is the Nancy Grace Roman telescope, formerly known as WFIRST. It's a near-infrared planetary detection telescope, and it'll be launched in 2027. And here it is in its clean room with its crew ready to be tested in a thermal vacuum chamber. And it's going to look at planets around stars that are much farther away than the Kepler mission or the, I'm not sure if, Kepler's here, I don't know what's in black, I don't see the graph, but the Roman telescope, which is formerly called WFIRST, is looking at planets that are much farther away, including free-floating planets that are being heated by some process and giving off enough infrared light that you could actually detect them even though they're not orbiting a star, which I think is pretty amazing too. And the goal of this technology, including the James Webb Telescope, is to analyze the light coming through the atmosphere of the planet and looking for the signatures of things like water, methane, You'll notice there's a, yeah, so water and oxygen here, vegetation looking like that, and CH4, methane over here, of course, you know what that comes from. The back ends of cows, pretty much. So if there are cows on these planets, we're gonna see a methane signature right there, absolutely strong as it could be. There are future missions planned as well, but this gives you an idea of what's going on there. So this is the answer. Are we alone? Well, it's when people ask me that on our outreach, I say it's hard to believe we're alone. There are more planets than there are stars. There are 200 billion stars in our galaxy and 200 billion other galaxies at least. The number of planets out there, multiply those numbers together. So it's likely that over 100 million Earth-like planets exist just in our galaxy, one of hundreds of billions of galaxies in the universe. So those are the two numbers. The number of planets appears to be close to every star, maybe even 2 planets. And the number of Earth-like planets is clearly greater than 0. So if any of these numbers are 0, of course, then of course the number of other civilizations has to be 0. But what has happened through the analysis of these two numbers is to prove that neither one of these numbers is 0. So that allows us to now look at all the other numbers here and decide whether any of them is 0 as well. So the Drake equation is kind of the guideline to our goal of understanding whether there might be life elsewhere in the universe. This is a really cool little animation. So this is what we call the orrery. So Ethan Cruz, back in 2011, put every planet orbiting a star on this little orrery here, and had them animated at the speed at which they orbit compared to all the other stars. So some of these orbit really fast, like this guy here, and some of them are fairly slow like this, but this is an animation of all the planets that were discovered by the Kepler mission at this time. And it shows you just how big the planet and its star are and how fast they're orbiting each other, not in real time, but compared to each other. So some are fast, some are slow. But none of them is that slow. Well, here's one that's pretty slow. But some of these guys are spinning around really, really fast. So those would be the planets that are really close. And the temperature is reflected by the color as well. So I wanted to close with that. So keep looking up, everybody. Somebody might be waving. And thanks. Yes, question?
As a practical matter, what can you detect? So, I mean, you've got a planet passing in front of the sun at, 1,000 light years away. And so there's a drop, yeah, but the transit time could be decades, depending on the size of the star and the planet and so forth.
Right.
So how do you really measure anything if you can't get a complete transit?
Well,
So is there a practical limit to this, or some expression that would?
yeah, certainly the planets that are closer to their star are going to transit the star more frequently because their orbital speed has to be shorter. Their orbital period has to be short if they're close to the star.
Right.
So we are biased to detect planets close to their sun more than those that are farther away. And also, the ones that are farther away have less chance that they'll actually pass in front of the star because the star is a finite size. And once you make the planet orbit really big, a slight incline off of the line between Earth and the planet and the star means you'll never see it pass in front of the star. So this is biased towards large planets that are close to their sun, that orbit quickly, so that you can have a detection, you can 3 detections within the lifetime of an astronomer, or even a few years, the lifetime of a mission, when your salary is still getting paid. So yeah, there's a lot of bias in this kind of analysis, but the amazing thing is how many planets I think have been discovered with all of those constraints, that it has to be big and close, and the star has to be close. The star has to be close to us. The planet has to be big enough that it'll block enough of the light that a sensitive detector can actually see the starlight dip. Yeah, and that's where the 1% comes from, and all of those
It's
different,
not just the orbital plane.
right. Well, thank you, thanks for your attention.
Let-
And turn it
Ladies
over
and
to-
gentlemen, T for Ted, but also terrific.
Yours is.
Amazing.
Sure.
The talent that we have in this organization,
USB-C.
that's why we have these
There's a
meetings.
USB-C
to
right
get
there.
That talent in front of you,
PowerPoint?
so that you
Yep.
can learn
Yeah,
and
okay.
they can share.
Oh, yeah, keep
All right.
Now,
sharing.
the talent right now is making some
Oh, there you
changes, technologically speaking.
Go back to that.
And
This
if you
doesn't
guys
work,
wanted to
so-
take about a 3 or 4 minute break, there's a restroom right down the hall.
final?
Yeah, I'm on.
While they're
yeah.
doing that, how about that? Let's do it, let's call it 5, while they do their thing. Okay? And you can chat if you don't need a potty break.
There's that. There,
Share.
and,
Share, yeah, share, should show up here.
okay, and I gotta get to there. Share PowerPoint. Oh, no, that's the other, yeah, sorry. Yeah, slideshow. Show, you are screen sharing.
Cool. Yeah, see, like, this is my AI.
Oh, yeah, that's right, you mentioned that, right. Now, let's see.
The habitable, the habitable zone in your orbital.
Technology to take their clear.
It's convenient to use this if it works.
Back to your
But
field.
it started working halfway through, but if it doesn't work, you can just push,
Compared to 1,000 years ago, we had storytellers who would draw images in the sand. You know?
page up and page down will work.
Yeah, yeah.
And,
The technology. Stu.
okay, this is working now. So it goes left, forward, backward. And that is the green laser if you want to use that. Yeah, there you go.
Okay. All right, so we're gonna need your phones out for my presentation when we get started here. What do we say, Stu, 2 minutes?
Yeah.
2 minutes, yeah, so we need your phones, like, there's a little more interactive what we can here.
What do you want us to do with our phones?
We're gonna do some QR codes.
Oh.
We're gonna play bingo. We're trying to play bingo.
We're gonna say DT.
Oh, that's not my phone, that's Ted's phone, okay.
So another that Jesse knows.
Oh, yeah.
From a year ago.
We are not a sponsor of that.
Okay.
Yeah. First, Mark Johnson.
So tell me something that we didn't know yet.
A lot of experience with that. It's not established itself. Move up there and
Which he discovered.
Yeah.
And he but I predict will be just somewhere of the universe is too close.
Have you done the Northwest or Southwest?
Is a microwave that occurred
Yeah.
100 million years ago, and that was the evidence of what was going on. Just is the microwave. So you can see the actual event.
Much smaller. I have it, so I couldn't answer.
There's so much of it covered in the
Stellar.
No one else knows that it is also the greatest of the gravitational basins in urban neighborhoods. Not the great attractor, not China, not even the Bella supercluster, which is pretty much we got a resident over here. But this object supercluster, which
This summer,
There's also in this community, we started our development.
Right, though, he was.
you can camp on my property, there's a hotel right in
Ella
town.
is the other end of the chambers.
And
This is all been covered by me years ago, and it's on the website.
Figure out what's in it.
Before it gets ridiculously hot.
It'll be 125.
I'm here till it's July.
What do you think about primrose and his gravity and heat?
Okay.
Okay, we are ready to return. So, as was mentioned, PAS has members who have talent, knowledge, passion, and the desire to share. And this guy, Richard Meyers, you know, a lot of us walk in the shadow of great people. And walking in this guy's shadow, he puts together our newsletter every month. And I'm telling you, it's a fine publication, and I think before he begins, we should let him know we like that publication. The floor is yours, sir.
Thanks, Stu. Thanks, Stu. So, yeah, I've only been involved in astronomy now for about 18 months. I mean, I've always had a passion about it, learning about it as a kid. But up until about 18 months ago, it's been at a distance from me learning. I've had a big C11 in my backyard, well, sitting in our bedroom, which really annoyed the wife for years and years and years. But I wasn't using it often. But I finally started using it since I met the organization here. So I was out on a trip a few weeks ago, and I picked up an audio book, which I'll talk about in a second. But it was more about our interstellar object here. So how many are familiar with Oumuamua? Okay, so there's some here. So let's find out how many. So I'm trying some new things here, which is probably be a challenge. But pull out your phones, scan the QR code here. Let's see if it pulls up the survey. Oh, it's not going to work, is it? Is it on yours? On mine? Ted, is there a mouse here?
No, there's no mouse, but.
Is it screen touch? Now, let me see if this works. Just clicking on it here. Okay.
That should be an actual.
Oh, actually, this is working. Oh, yeah, this is not gonna work. Okay, results. Can I see the results? Let's see the results here. Nope. That's what I was afraid of. We tried a few things. We learned a few things along the way. Let's see. Yeah, unfortunately, that's not going to show up here. Okay. Oops. All right. Just donate. Share this. We tried. Nope. Okay. Okay, yeah, because I had to switch my machines around here, but yeah, all right, so I'll try that again. But you pulled up the survey on your phones, click something, so I'll have the data when I get home. And the other one I want to try is bingo. Let's try this one. Let's try that one. So it should pull up a bingo card that you can follow along with for the rest of the presentation here. Oh, got it. There you go. All right, cool. So you just click on things.
Even from this angle, I was able to get it.
All right, so this is our interstellar visitor. Right, that is the best image that they've taken of this object. Start with calling it by an object. Our first interstellar visitor. Oumuamua. So again, it's you know, tiny little, you know, a couple little pixels there, and you know, the camera is, you know, taking a picture through the sky, so all the stars are blurred as they were trying to follow this object. And you know, this showed up. Pan-STARRS in Hawaii detected this. Which is you know, a Hawaii messenger arrived from far. So this is the first image they found, and then they went back and looked at it and said, "Oh my God, look at this! It's something we've never seen before, and let's dig into it and see what it is." So you get a rapidly moving object through our solar system. So they didn't really know what it was initially when they found it, detected it. But they did see that with the speed and its angle where it was coming from. So what comes to mind? See the audience participation.
That's a good one.
Yeah, that was my first thought too.
Oh, yeah, okay. Yep, so exactly. So when it first you hear it in the news, right, this is the first thing that popped into my mind is the book by Arthur C. Clarke, Rendezvous with Rama. Great book. Is whoever hasn't read it, I would definitely highly recommend picking this up and reading about it. But it is exactly what happened, an interstellar object that they went to investigate. But this was a huge little living hollowed structure city. So how does it you know, map to what we found here? So this is the animation of the path through our galaxy. So it came in from a high up, I guess northern angle there, and around the sun and then out. So it originally from Vega, right? That's what is it, like a million years ago or 100,000 years ago, something like that. But the direction where Vega is today, not where it was 100,000 years ago. So there's a lot of, you know, changes as the galaxies and the stars are moving. So they're not exactly where it actually started from. But it comes in, goes around the sun, and they didn't pick it up till it actually was leaving our galaxy. So they had a very short window of time to take a look and process and determine what this object was passing through our galaxy. And it closed 15 million miles from Earth, inside the orbit of Mercury and then around the sun.
Sorry.
Yeah.
You said that our galaxy is not an intergalactic object, is it?
Yes.
It's a separate
Solar system.
So from the other solar
Solar
systems,
system, right.
yes, outside of our Milky Way galaxy.
So that's why it had such a strong, the sun's gravity had such a strong impact on its trajectory. It passed inside the orbit of Mercury.
Yes,
Oh,
yes.
so that's a big change.
Have
Yep.
they made any estimate? Okay, so
You're probably jumping ahead.
Okay, it's moving out here in space.
Yes,
At some point, it's going to start to feel our sun, right?
I will cover that.
Okay.
I will cover that. Yep. Okay. So again, the object's coming through. The astronomers jump into action. They look at it. They try to rally the scopes, and you know what is the first thing that comes to mind? A comet or an asteroid for them. So again, they look at it. Is it a comet? Right? It has. They're trying to analyze it. You know, is it ice? Is it dust? The brightness of it, the orbit, the surface, and the characteristics of it. So it's sort of a comet. So it gets classified, I think, initially as a comet. And then they decide, maybe not. Okay, so maybe now, since it's going past the sun, but we don't see any tail, and it's reddish, so no, well, maybe it's an asteroid. So then they reclassify it again as an asteroid. So you're going back and forth. They're really not sure, so they started digging in even deeper. Now, given this, right, they had a window of, I believe it was like less than 30 days, because the brightness was dimming at an exponential. I think it was a 22 when they first discovered it, and it just got dimmer and dimmer and dimmer as it left the galaxies. They had like a very short window to analyze it. So what they did is spectroscopic measurements. So they ran different Spitzer telescope, but they repurposed it, and you were able to get some time on it real quick for like 3 days to start imaging and taking pictures. And which is the laser, the first one? Okay. Yeah. So what they did is again mapping the wavelength. This is the visual end here, and then the near infrared here in red. They mapped it against known objects, right? Different types of asteroids, different types of comets. So now they see if they overlap in them here, these dots of the object here, it is sort of matching up more like an asteroid. Okay, so we're back to, maybe it's an asteroid, still maybe it's not a comet. So again, a lot of unknown. Here it is. They had 30 hours to look at it before it disappeared and just make their analysis. So again, it sort of more tilts toward a comet type versus the asteroids, different colors, so it's more reddish. So the higher spectrum here is more of a red, which they detected. And so from these images, what they sort of, again, this is where you get biased, super biased by the images, the composites they put out there for us, right? There were two theories here, right? Is it elongated or flat? And so these, I think these are the images everyone's seen published out there. So again, based on the spectral imaging, visual imaging, they came up with some rough measurements of this object. It's about half a mile long. Maybe it's a long and narrow versus anything they've seen. So it's very little different, but could also be an oval or cigar shape. So. So they're measuring this thing, right? And they're trying to figure out, I left my other object at home, the flat one, as it was going through the space, right? It's tumbling different directions on 3 different axes. This thing is, they determine is tumbling through the sky, trying to figure out what it is. So again, not super easy. It's super, far away, and you'll have the 30 hours to analyze it. Here. Yep. Okay. So he rotates. So they determine the rotation of this is roughly every 7 to 8 hours, depending on which scientific papers you read. And there are a lot of them out there, right? A lot of them contradict each other. There are all these theories about what it was and why it was turning and what it was made out of. But this is, so much what they settled on is this is what we know at this point. And so. Let's see what it's like here, and the color of the surface, right? Again, a lot of red. So they're thinking maybe it's a solid object, reddish, iron-rich, metallic subject, based on some of the reflectivity of the color and the surface of the object itself. So these are, sort of what we knew, right? And then this is where it got interesting to me. An author. I guess he was a Harvard. I think he was at Harvard. Avi Loeb. He came out with this book, New York Times bestseller, and where he talks about maybe this was a first sign of intelligent life beyond our galaxy, and it's just super. It's an interesting book, right? He comes out with a couple different arguments. That maybe this is an extraterrestrial because things don't really match. And he has like 3 areas where he points out that it just does not make sense of what we're finding out there, and maybe it's something else to have an open mind. So again, part of the book is about this, but the other half of the book is about understanding science. So it's a really interesting book and how you get into research. So if you have time, I definitely recommend picking it up. So we're going to drill into these 3 objects here, right? So based on what he saw here going to the cloud, right, there was no commentary or outgassing observed for the object. So when it passed by the sun, a normal comet, you have those tails, nothing there. Unusual motion, right? So again, when it passed by the sun, it accelerated. So they detected a bit of acceleration passing by the sun. And then the reflectivity of the object was very, very bright. So it's not something they typically, when it was a comet or a meteor, this was much brighter than that. So based on a couple of these things, you thought, maybe it's come up with its own ideas that it's extraterrestrial. So again, I just, threw this one, right? This is we had our pit peak last week or last month in here. So this was interesting, the wind telescope down there, right? They were monitoring it, and they didn't see any kind of a comma when it passed after the sun there, after passing by the sun. So they didn't detect it. I just did this one because a local planetary observatory, and they were here last month, so it's kind of cool. So again, why no trail, right? So typically a comet, right, if it's passing by, if this was a comet, right, you know, solar heating, ice sublimates, and it creates that gas or dust and forms the tail. That wasn't observed, right? So, let me get here, yeah, okay, here it is. So again, maybe there was some hidden gases, something that we didn't understand, right? Our Spitzer wasn't enough to detect, right? So maybe it was too faint. We only detect certain types of gases, and maybe it was unknown gas. You know, typical comets have those outgassing, so they're always, you know, detected. So maybe this is something new. Maybe it was some type of exotic ice that, again, not able to detect. I mean, whether it's hydrogen or nitrogen, frozen nitrogen. Sublimating, so it was going right from a solid to a gas that we weren't able to detect. Another area, let's see, and then this is the interesting one, right? Maybe it was a light sail or some kind of space debris, right? Because he was able to, so you know, it accelerated. They had no observable gas detection there, or no dust on the tail or anything like that. Maybe it was some kind of interstellar light sail passing through, you know, based on the dimensions and characteristics. So I'm shaking your head, no? No, no.
We already had a lecture
Oh,
talk about
okay.
this
Oh,
years ago.
Yeah, when it first happened, yeah, so.
Yes.
Okay. Yeah, so it's interesting here, you know, identifying that, maybe it is a light sail. Motion acceleration, right, as I mentioned, right, so it went past the sun, you know, usually, you know, you have a gravity assist, and they detected an increased speed, right, so why did that increase in speed? And a couple of, you know, again, same reason, right, usually the gas, right, or dust will increase, or, you know, gives it a little jet thrust to the comet to accelerate it, and none of that was detected. So maybe there was some kind of you know, internal forces, heat, some kind of heating effect, where, you know, one side was heating more than the other, and when it rotated around, it cooled it, or it pushed it into another direction. Another one was, again, back to the hidden outgases, right? So they didn't detect anything, but maybe there's something we did not see, or our scopes out there are just not able to detect it. They're not that accurate enough. Just they're looking for big particles. The tiny particles are not observable. Nitrogen gas, right? Something exotic. Maybe it was some kind of a fragment of like a Pluto, of a planet that, you know, broke up somewhere or was flying through the system. But all these have, you know, these are, for everyone you read about, you can read about a study that says this is not possible because of this. So, you know, again, nitrogen is very fragile, and it will evaporate in space over, you know, thousands of years it would have taken to get here. So there are just, you know, different ideas around what made it possible. Another one, right? So, you know, maybe this was some type of fragment of something breaking up and going through another galaxy. You know, this is like Shoemaker-Levy 9, when it, you know, the comet broke up, crashing into Jupiter, you know, years ago. So maybe this was, you know, again, some piece of that was flying through our galaxy and breaking up at some point. But again, right, motion, right? So again, the concept of that solar sail, right? So when it's going past, it's picking up a little tiny boost on that solar sail, giving a little bit of acceleration. So this is again back to, you know, Avi's, you know, his book here. This is just again a theory, right? Nothing's been proven. They're just, you know, trying to get you to think about what is possible, what is not possible these days. Any bingos yet? No bingos?
4 more.
Oh, 4 more. Okay.
This is coverall, right?
Yeah, they should all be in.
Coverall, not 4 in a row.
That four in a row.
Oh, I got a lot of those.
Oh, 4 in a row.
Nothing.
Oh, we could do all. Okay. Motion acceleration, and then there was the shaped reflectivity. You know, again, was it a scar or was it a pancake? The tumbling, so they had shiny surfaces, which could be from, you know, metal-rich some super compacted ice. You know, if you ever been to like some glaciers that hardened blue, 1,000-year-old ice is really compact and really shiny, or just again something else like Pluto, the exotic nitrogen. So again, another artist interpretation of what it may look like, but a little bit brighter, a little bit more red. And again, no tail. So again, you keep coming back to why was there no tail? Shape and reflectivity. So they did get some good data here. So the bunch of different observatories was able to collect, the reflective pattern here over I think this is like 3 days of the data that they were able to collect. 3 days. And this is sort of an interpretation of that reflective pattern here. So you can see up and down, up and down, up and down as it was rotating around here. But this is just like the one simulation, the 10-to-1 ratio as elongated versus trying to do it as a pancake or some other object. And this spinning, wobbling motion as they processed and went around. So again, so those 3 traits, Avi said, okay, maybe this is extraterrestrial, like, because nothing else fits. So what are your thoughts? What is everyone's thoughts on that?
Nitrogen.
Nitrogen?
Solid nitrogen.
Okay.
A lot of asteroids have been shown now to be binary contact objects,
Yes.
elongated. So it's not, if it is an asteroid that was ejected from another solar system, it's very likely that it would have been a binary object to begin with and would still be one, so that would make it elongated as opposed to.
But at that large 10-to-1 ratio
10-to-1 is way bigger.
than anything we've
but at
seen,
least-
yes.
At least the binary is much more common than we ever thought. That's the only point.
Yeah. Anyone else? Paul?
When this object was first detected, we did have a professor from ASU do a presentation on
Yeah.
this object. I remember one of the things he pointed out was they couldn't detect any gas being expelled from it. So he looked through the gases that we couldn't detect, and one of them was nitrogen. So he suspected there was some kind of nitrogen source on it that was giving it some extra, little extra.
That would,
out of the solar
couldn't
system.
detect.
Covered some-
But there's,
some lead points, but that was just a few months after.
that was a few months after it happened, yeah.
A second object, a discovered object was discovered after that.
Keep jumping the
I
slides.
suspect, if there are more planets than stars, there's probably tons of crap just flying around the
Yeah.
galaxy at the moment in all sorts of fragmented forms, of which there's,
Yeah.
just the first one we saw, there was a ton of it.
Well, that's exactly. So yeah. So Paul. So if you go back now and read some of the research paper, they don't think that the nitrogen, frozen nitrogen, would have survived as long as it necessary to come through here in it just the nitrogen states. Maybe there's some other chemical interactions going on to try to harden it a bit to survive. Again, they don't know. I mean, we just don't know. So I read a lot of theories and counter theories. Yeah.
From the data, I mean, I'm assuming that obviously they tracked it and how it came into the sun and angled out. Were they able, does that give them enough data to calculate the mass?
No.
No.
Yeah, so one of other Avi's Loeb's theories was that maybe it was a hollow object that was heated passing by the sun to give it that extra boost, like Rama. It's hollow inside or something. Yeah.
Nitrogen is one of those gases that has a higher temperature at which it stays solid. You could lose the helium, the hydrogen, and the others, and still keep that core for
Frozen.
the longest time. It'll be the last thing of several to evaporate.
But it would evaporate over thousands of
Some of it.
years to get here, right? Some of these.
But you're sacrificing
How big
other
it was,
gases
yes.
along the
Yep.
way.
Yeah, so there was, in the meantime, there was a second object, Borisov, was detected, in the 2019, amazingly, only 2 years later, which, considering 2017 was the first, and then 2 years later, you actually find your second object. Again, but this one, as they were able to track it, had more of a appearance and conformed more as a comet. It behaved like a comet, it had all the traits of a comet. So now which was the right one, or is it Uma, and something we don't understand yet, we haven't encountered, or are there gonna be more of them we're gonna encounter in the future? Right, if you compare the traits of them, right, you have Borisov, had the tail, no tail, and shape, cerebral shape, elongated, rich and dusty composite, unknown, rotation, it's stable, and rotation chaotic, and then, again, comets, tend to be darker, and this is super shiny. So it's, interesting to find the second object 2 years later. So again, decoding here, so let's see your hands, natural or natural, anything people think is natural.
Yeah.
Majority, artificial. No one?
We're astronomers.
No. Well, but artificial doesn't have to mean alien, right? It's just something we don't understand yet. Well,
Was it Carl Sagan who said that extraordinary claim?
No, he-
about
he-
extraordinary evidence?
Yes.
Yeah.
Did you look at my presentation?
Oh, okay.
Yeah, you're like right on. Okay, so so no direct evidence. So we have some unexplained objects. There is a natural explanation exist, but it doesn't fully match, right? It doesn't fully conform to the object itself today. Again, our first selection bias, right? We don't understand what we're seeing yet, right? We don't have the tools. The technology is still, again, it's come a long way to starting to observe things, and I'll show you our last piece here, what the future's going to look like in a second. So again, there's a lot of stuff we still don't understand with that short window we had to observe it and analyze it. But it sort of makes you think, right? The universe is under no obligation to make sense in the first try, right? We don't know. I think that pretty much sums it up, right? But again, for artificial, it matches like predicted characteristics of a light sail. So you sort of keep coming back to that. Maybe there's some other type of light sail that we haven't, figured out how to build on our planet yet. Maybe some other technologies figured out how to build a really thin one, and then somehow it got junked up in space and just floating through. The one slide I forgot to put in here was that they did try to listen to any kind of radio, any kind of transmissions from it, and they did not hear anything in what we typically monitor. So they didn't hear anything coming out of the object as it passed through. Yeah. So this is, again, do we have enough evidence here? I don't think we do yet, but it's definitely interesting to think about it. What maybe it is, we just don't know yet until something else comes and passes by. So how are we going to do that in the future, right? So this is amazing telescope going down in Chile here, the Regular Observatory, or what it used to be called LSST or something like that. They renamed it. It's coming online sometime this year, and it has a 3.2 gigapixel camera, which is tremendous. So they're going to be able to scan the night sky, like supposedly every 3 days, to be able to scan the entire southern hemisphere every 3 days in 6 different filter bands and analyze the data. So they're going to get. So by 2030, they'll be fully operational and running, and they expect to detect, 10 objects a year possibly passing through here, which is, super impressive. So again, back to Occam's razor, right? Simplest thing is usually the best. So again, it's, I think, like everyone else here, right? This wasn't alien because we can't see it yet, but some kind of natural object that we don't understand yet. So let's see, how do I do this here? So what I think it is.
Get your notebook out.
Yeah. Doomsday Machine.
Star Trek.
All right.
Yeah.
So you got solid Trojan.
3, 2, 1.
Big ideas don't come easy,
Come on. Yeah.
but when you get one, use them when it's clear.
Come on.
You can also touch the screen on Skip. It's touch sensitive.
Here it goes.
It's good.
Ready?
Oh, come on. Why are you not playing? There it goes.
Passion, we've got determination. Like if we set a goal for something, you better believe it's happening.
Touch the word skip with your finger. That'll work.
I feel like a content
Just pause it.
was all about entertainment, being fun.
Yeah, just pause. It keeps pausing it.
Oh, yeah, it's probably pretty slow.
Let's try this one more time.
So you think you know Wix? Do you really? First up, we've got Shake Video
Yeah, it won't skip.
masks. You can use different shit.
Oh, because you're looking at the Zoom version. Yeah, that's probably why. It's, yeah.
No. Well, this is the presentation. No, it's okay. All right. Okay. All right.
Create completely different vibes and aesthetics. Or you can create your own graphic.
Where's the Zoom go? Let me get back. What are we looking at? Where's the Zoom? I lost the Zoom meeting.
Use the shape composition here. Just import any SVG file and set it as a shape mask.
How do you get back to full screen? Is that it? Ted, how do you get back to the full screen here? You see? I lost the zoom here in the desktop. That's not it. This is screen sharing. Documents.
Nice. Next up, we'll keep it moving with the upper box. You can use it to animate any element and create these really eye-catching interactions.
Okay, there we go. All right. All right. So the quiz won't work, but yeah, that's all I got for you tonight. So discussions. Alien. Can't wait to the next one. Paul.
I remember, I think the name of the professor that gave a presentation on this when it first came out was Professor Stephen Dench. One of his background or his research is planetary formation, not only the formation of planets in our system, but also around other stars. And what he brought out was that as objects are forming in other planetary systems, things get thrown out. And he surmised or speculated that this object was something that was being formed, but it got thrown out before it could be incorporated into something else. So it may be a piece of something or the beginning of something else.
Yeah, like Pluto in process, the icy planet being thrown out. But again, you go back and read some of the more current papers, like the forces necessary to do that are tremendous to throw something out and cross the universe like that. So, maybe around a supernova, something that has a huge gravitational pull to spit it out or something. It's interesting if you go. Yeah.
The formation of planetary systems is very chaotic.
Yes.
So there might be enough.
Three body problem is what the movie, right? It's something that's big enough to spin it out.
Plus, you can look in our solar system and see moons orbiting retrograde that had encounters with other moons that reversed their orbits or tossed out the object that was the reversing object.
All right, so who got bingo?
Yeah. I've always thought,
You gotta,
I've always thought that for every comment that comes in from the org file, there probably is another one that got thrown out of the org file. They did some sort of gravitational binary dance. And so, not surprising that
Well, I also want to point out that jumbos, Jupiter mass binary objects have been found in lock globules without a star. So those objects can toss out anything else that was formed with them. Lots of sources, but you can't Von Donegan us with, it's an alien that did this because you don't understand it.
it is. Pick up, obviously, Alviova's book. I think you'd appreciate it. So he doesn't come out and say it is, but he just let you draw your own conclusions. You know, could it be this technology? Maybe. Maybe it is a light sail. Maybe we don't understand how they made that technology yet.
We
So
should
it's
learn how to make
speculation.
light sails so that
And they
we
are.
can-
There's another group, I think they're looking at 2030 to try to launch a prototype. And
Yeah, I think the Space
Point-
Society did launch one, but it tumbled out of control in
Yeah.
orbit.
they want to get up to 0.8 speed of light is their goal.
isn't there some theory that you could catch up to this thing with a
Yes,
light sail
yes,
and a laser on Earth pushing it?
Yeah.
yes, yep.
With
Theories.
the laser melted.
Yeah, so that's one, and the other actually, the research I saw is that they want to be able to put something in a Lagrange point
Yes.
around us, so the next time something comes by, they have a craft available to go out and investigate it. Which,
Grab it with a net.
yeah, and then, you know, with CubeSats, you know, these days, they're so small, right? It's more cost affordable for them to do that.
All right.
Yeah, all right, well, thank you guys.
You have to help me turn this
Yeah,
screen off.
I gotta figure to turn this off. Sharing screen is stopped, window is closed, end meeting.